Thank you very much. Your Excellencies, distinguished guests, ladies and gentlemen, good afternoon and good morning or good evening if you are following us on internet, depending on where you are in the world. Today I would like to come back on the history of CSP by reviewing some important projects at pilot scale or industrial scale. But first of all, why thermal storage? So why we are talking about storage today? Because it's a key feature of CSP. So if you look at this very interesting graph that I found on Navigant Research, it's the energy storage power capacity by technology and region for the last quarter of 2018. And we see in green that thermal storage is dominating all over the world, closely followed by electrochemical storage, which is in gray. So we still have an advance in front of electrochemical storage. Why? Because we are still cheaper. For how long? We don't know, but we are cheaper. So it's difficult to give some values, but I found this reference here where I'm talking about 33 times cheaper than electrochemical. I personally believe it's overestimated, but let's say that we are at least 10 times cheaper than electrochemical storage. So we have talked about CSP today, and CSP does not compete with PV. It competes with other dispatchable powers such as natural gas, for example. And why we have seen, I think Chuck and Cyril presented this duck curve this morning, and we have a big problem of peak demand in the evening. So if we store energy during the day and discharge this energy later on, we can answer to this peak problem in the evening. And basically, that's what's going on in Dubai. This is a project from Dehuaa, which is Dubai Electricity Water Authority. They are deploying 5 gigawatts of solar energy, among which 4 gigawatts will be PV and 1 gigawatt will be CSP. Same approach in Morocco, where they're deploying 1.5 gigawatt with 910 megawatt of CSP. So clearly, actually, PV and CSP are complementary. So now, how to store thermal energy? We have different methods, some physical processes like sensible heat or latent heat, and some chemical processes. To date, all the commercial CSP plants are using sensible heat storage, where you store energy in a material which can be a liquid or solid, and you use a delta T to store this energy. So basically, the energy you store is the mass of your storage material, M, time the heat capacity, CP, time the delta T between the charge and discharge. So I will review some of the projects. Of course, it's a non-exhaustive list. So forgive me if I do not mention one project. I will use this graph, which is from this paper from Xavier P. in 2013, and they have separate two periods for the CSP development. The first period from the 80s to 2000, and a second period from 2006 to nowadays. So if you look at the evolution of CSP plan from the 80s to 2000, you have mainly 3 pilot scale projects called Solar One in US, Themis at the same time in France, and Solar 2, which is basically Solar One, which was converted to another technology. And in parallel, you have a commercial project deployed in US with the CEGS project. The first approach was to use synthetic oil as thermal energy storage material. And this is what was used in Solar One and CEGS One. So in Solar One, they decided to use a single tank storage that we called thermocline. So we called thermocline because you have a gradient of temperature between the hot heat transfer fluid and the cold heat transfer fluid. And to reduce the quantity of oil inside the tank, because the oil is expensive, they used filler materials such as rocks and sand. So you have here a picture of the plant, Solar One, with a single tank. They faces two major problems. The first problem is the so-called thermal rashing. So when your storage is hot, the steel tank is expanding, and so the filler material is settled down. And when you discharge, the tank becomes colder, so it shrinks, and you may break the tank due to the mechanical stress. Another problem is the direct contact between the oil and the sand, which could degrade the heat transfer fluid. At the same time, they deploy the CEX project using a two-tank oil system. So basically, you have a relatively cold tank of oil at 240 C. You pump this oil inside the solar field, and you reach 307 C and store the hot oil in the hot tank. Unfortunately, this storage system was destroyed by fire in 1999. Now, in parallel of the synthetic oil approach was developed the molten salt approach, firstly in Themis in France, and then, as I told you, Solar 2 was converted from Solar 1 to Solar 2 using a similar technology. So here you have a picture of Themis, which was 2.5 megawatt electric, and here a picture of Solar 2 with now the two tank, which was 12.4 megawatts, sorry. So the concept here is a two-tank molten salt technology in a direct way. Why we call that direct? Because you have the same heat transfer fluid for collecting the heat and storing the heat. So you pump the relatively cold salt around 290 C from the cold tank, bringing it to the receiver to collect the heat. Then it reaches about 565 C, and you bring it back in the hot tank where you store it. And once you need energy, you just pump the hot salt from the hot tank, go to the heat exchanger to produce the steam for the turbine, and bring back the cold salt into the cold tank. In parallel of this molten salt approach, then we move to the second period of deployment of CSP from 2006 to now. And the first project was developed in 2007 by Abengoa Solar. It's a PS10 in Seville. And the idea was to use direct steam generation, which is also currently used in a commercial linear Fresnel system in France. I will come back on that. So PS10 is here. It's a direct steam generation, which means you pump liquid water directly into the receiver where you evaporate the water and create saturated steam that you can store in big tanks. So you can see here the 4 tank of PS10 where the steam is stored at 250 C, 40 bars. However, this is for a short period of discharge. For example, this is 30 minutes at full capacity of 10 megawatts in this case. The commercial project in France, it's the world's first Fresnel system, including a storage system. It's also the first commercial CSP plant in France. And it's a 9 megawatt electric, and currently it's under commissioning. In this case, they are using 9 energy accumulators that you can see on this picture for a capacity of 4 hours of discharge at full capacity, 9 megawatt. Then we have to wait 2008, where Andasol 1 was deployed, and later on in 2011, Dehuaa Solar. So these two plants were using the molten salt technology. So Andasol is the first commercial CSP plant using the two-tank molten salt technology. using the binary conventional nitrates, sodium, potassium, and with a storage capacity of 7.5 hours. So how it works, you have it's called an indirect system. Why? Because you have the synthetic oil in the solar field to collect the energy. And then once you have too much energy, you come into this heat exchanger to transfer the heat from the oil to the salt that you pump from the cold salt to the hot tank. And at night, when you need energy, you do the contrary. You come with relatively cold oil and discharge energy from your molten salt, and the oil can go to the steam generator to continue to produce electricity. Here you see the Andasol 1 power production versus time of the day and versus the season. So we clearly see that on the blue curve here, this is the winter. Of course, the day is shorter and the DNI is lower, so we produce less during the day. And this small shoulder here is when you start to discharge the storage system. However, in summer, you see that we start to produce much earlier. And when we discharge the storage, it lasts longer. So why I wanted to show you this graph, because when you design a storage system, you have to make a choice, and you usually choose one season. So the question is it specific to Spain, or can we apply that everywhere in the world? So I asked one of my students to do a quick study. So on the left, you have the DNI in Spain for Andasol. So in blue, it's in January, and in red, it's in July. And on the right, you have the DNI in Abu Dhabi, where we are penalized during summer because of aerosol in the atmosphere. So our DNI in summer should be much higher, but it's not. However, in winter, we have a much higher DNI. So you see that the difference of DNI between the winter and the summer is much higher in Spain than in Abu Dhabi, which brings me to my conclusion that the aerosol that are considered as a drawback, in fact, could be an advantage for the storage system, because when you design it for a longer period of time in the year. And to prove that, I asked my student to do a case study. What if we would have built Andasol in Abu Dhabi? So in blue, you have the production of energy from the real Andasol in Spain, and in orange, this virtual Andasol in Abu Dhabi. You clearly see here, I forgot to mention that we use the SAM software from NREL. Here you clearly see that in summer, you have a decrease of, we are penalized in Abu Dhabi because of our aerosol, but in the rest of the year, we are producing more. And if we have a 13% higher DNI per year, we are producing more than that, 33% energy. Why? Because the storage system is optimized and is used on a longer period of time. So the capacity factor of the plant is increasing. If we look at the CSP plan deployed all over the world, we see that in operation, the green is parabolic trough, is a mature technology. But if we look at the announced or plan project, the purple one is tower. So why the tower is taking the lead over parabolic trough? Because we want to reach higher temperature to increase the efficiency of the power block. And also, if you reach higher temperature, you have a higher delta T, so you will store more energy. So that's explained why in 2011 was deployed Dehuaa Solar in Spain, a plant built by Sener and Masdar. It's a real breakthrough in CSP. Why? Because it's the first solar plant in the world to produce electricity 24 hours a day, thanks to 15 hours of storage capacity. So here you can see data from this plant. So in red, you have the production of electricity over 7 successive days. And we clearly see that we are able to produce almost constant power thanks to CSP. The green is power in the receiver, and the blue is your storage and discharge of the test system. This technology was recently upscaled from 20 megawatt to 110 megawatts in the Crescent Dunes project in US, in Nevada. So you see 110 megawatt with 10 hours of storage capacity. So now this technology is mature, and we are seeing more and more projects. One which is remarkable is the project of Dehuaa in UAE. They are building 6 parabolic troughs of 200 megawatt each, plus a tower of 100 megawatt. This will be the highest tower, power tower in the world, with 260 meter height. I'm not convinced that this is the right approach for UAE because of this aerosol problem, but this is a remarkable project. Then in where I'm here. So in parallel, in 2009 was proposed by Germany a system using air as heat transfer fluid and ceramic as a storage media. So this is a unique power tower, which is now in the hand of the DLR as a research facility. What is remarkable in this plant is that they are using air at 680 C. So we are trying to reach higher and higher temperature. And the storage system is made of silicon carbide honeycomb structure that you can see here. We don't see new plan using this technology in the pipeline, but I think using air and ceramic is really interesting for the future. Now to conclude this presentation, I would like to show you a few other promising solutions which are not yet either in a large-scale pilot system or commercial system, but that are of interest. The first one is the idea to use concrete storage, which was initially proposed by DLR and Zublin in Germany, and then later on a new design and new material was proposed by Energy Nest, which is a company from Norway, and we have worked with them to test this 1 megawatt hour prototype. So of course the advantage of concrete is the cost, because concrete is cheap. However, you have to consider the steel heat exchanger, which compensate a bit the cost, but in general you are able to decrease the cost compared to molten salt technology. Another interesting approach is to use a direct absorption receiver. I wanted to show this project because I know that the Cyprus Institute participated in the initial concept proposed by MIT and published in 2011. We have recently validated this concept at pre-industrial scale with about 4 tons of molten salt. So the idea here is to concentrate directly the molten salt, the light, sorry, into a molten salt bath. So you don't have pipe, so it's convenient, for example, to in the morning when you focus, you don't have to take care of the thermal expansion of the pipe because you don't have. And we got a very promising result that will be published soon. Finally, I would like to mention this project by Sandia National Laboratory, mainly, and other actor in the world. But the idea here is to use particles such as sand. The advantage of sand is that it's cheap and that can reach very high temperature, around 1000 degrees C. In this prototype, they were able to reach 700 C with 80% efficiency, which is, I think, very interesting and promising for the future. And with that, I will conclude my presentation. Thank you.
The tendency is to go to bigger and bigger infrastructure and to centralize, in fact, the production of electricity. It does not exist a research to go in the other sense, for example, for supplying electricity for a village in Africa? Or
yeah, that's a very good question. So we are working on that, for example, with Clean Energy, which is now called Azilio. We are collaborating with them. They have a very interesting technology where you could have a dispatchable system at a smaller scale using Stirling engine. So Stirling engine is very efficient, around 30% efficiency. But the main problem was up to now there was no storage technology for that. So I think this Azilio approach is interesting. And we have other collaboration, for example, with Dehuaa Solar, which is a startup in Dubai, deploying a smaller scale system. I cannot tell more now because it's under construction, but yes, we are looking at that. We have our partner Masdar deploying special project in isolated island or in Africa where they do not have grid connection and they need independent system, including storage. So yeah, the answer is yes.
Actually, the picture on the poster, and we have a presentation later on, is intended exactly for that. Downscaling CSP down to community size with cogeneration and storage. And there will be presentation later on exactly targeting the opposite end, namely downscaling the advantage of CSP to community level issue, which is a special market. Is not the usual market, but a big need for islands or the third world. And I believe there will be an excursion on Saturday. I don't know, Manuel, is it arranged for those that want to visit the facility? It's operating.
It's an option. I have the micro and I have a question before. Can you show because I am from Seville and I've been doing a lot of things with radiation. Can you show the data again in Seville? Because I saw something that I would like to.
Something wrong?
Well, no, not wrong.
I will go back to my student if it's wrong.
This is
this one.
These are,
this one.
No, the one, the previous one, the one that shows. This is instantaneous. This is the average.
Yeah, I think it's average DNI over the months.
Average is average because the problem is that we have a lot of cloudy days. Let's say in Seville we have more than 2,100 or 2,000, more than 2,000 kilowatt-hour per square meter. And in winter and also in the Plataforma Solar, the days when you have a good day, you have more radiation. You have than in summer, more clear days. The same happen in Pamplona. You can even in Pamplona you can get 1,000 watt per square meter. The thing is, this is an average. If you have one day that is completely cloudy, and we have many cloudy days, this is. But you are comparing maybe instantaneous.
No.
This is also average. The one from Abu Dhabi is average.
Yeah, I think both are average. My intention here was to show just the difference between.
If it's average, you are completely right. But I thought that was instantaneous. Instantaneous is you get a very good radiation. The thing is not too many days.
Sorry. Still 4 minutes for questions.
I would like to complete my answer on your question. And especially with this project here, 260 meter. My personal feeling is that we have to go also in the reverse direction by using smaller tower. And this is what we are doing. We have signed an agreement with 24/7 Solar, which is a spin-off from MIT, proposing also small-scale tower around 300 kilowatt electric using Brighton cycle. micro turbine. And also, I'm aware of a project in Australia with Vast Solar, where they are also using a small scale tower. So I believe also for project in region like Middle East, where we have a lot of aerosol, the multiple tower concept, to my point of view, could be more attractive than a huge tower where the last heliostat is at 1 or 2 kilometers. And so we will see also multiple tower concept. I'm convinced about that. Thank you.
One question, okay.
Yeah, Luis Crespo, regarding the picture where you, at the very beginning, you explained the comparison in cost between batteries and thermal, I'm going to provide some additional information during my speech this afternoon, but I can tell you that you were hesitating regarding the price of 30 times or 33 times that you explained. If you compare just in terms of kilowatt hour, no matter whether it is thermal or electric, perhaps this number is more or less correct. If you compare the equivalent of capacity, cost per kilowatt hour electric equivalent of this thermal capacity installed is in the range of 10 times, but still, in terms of equivalent electric, we are 10 times cheaper than batteries. And now this can be, very, very easily being compared by the big project that Tesla has already developed in Australia, $70 million, $75 million for 100 megawatt, 1 hour of storage. You compare with the molten salt in towers, mainly in towers, not in parabolic troughs, you will find that our prices are in the range of 50, while in Australia the prices are in the range of 500. So it's 10 times lower.
I agree.